The number of black holes in the observable universe is probably somewhere in the range of 10 to the power of 17. That's 100 million billion. Give or take several orders of magnitude, which is a phrase that should bother you more than it usually does when scientists say it. Several orders of magnitude means we could be off by a factor of 1,000 and still be considered in the right ballpark. We're not sure. The detection methods are indirect. The census is incomplete, and a meaningful fraction of stellar mass black holes are invisible against dark backgrounds with nothing nearby to give them away. So when someone asks what happens if they all collide, you're starting from a foundation of we don't fully know what all means. That caveat aside, the popular image of a black hole as a cosmic drain actively pulling things in is wrong in a way that matters. Gravity doesn't work differently around a black hole than around any other mass. If the sun collapsed into a black hole tomorrow, same mass, just compressed, Earth's orbit wouldn't change. Not slightly, not at all. The gravitational pull at 93 million miles would be identical to what it is now. What makes black holes dangerous is the density, which allows you to get physically close to an enormous amount of mass without a solid object stopping you first. The event horizon is the point where escape velocity hits the speed of light. Inside it, the geometry of space-time is oriented such that all paths lead inward. It's not that you can't go fast enough to escape. It's that outward stops being a direction you can travel in. That's a hard thing to visualize. And I'm not sure the common explanations actually help people understand it versus just giving them a new picture to nod at. Sagittarius A star is 4.1 million solar masses and sits 26,000 light years from us at the center of the Milky Way. It's accreting, consuming material continuously at a rate of roughly 5 lunar masses per year, which for a black hole of that size is negligible. Starvation level feeding. In 2013, a gas cloud designated G2 passed close enough that people genuinely expected to see something dramatic happen. There were papers written in advance. Observing campaigns were organized. The cloud got tidally stretched and partially disrupted. Some material fell in, and the resulting activity was, and I think this word is accurate, boring. No dramatic flare, no sudden brightening. Sagittarius A star barely registered the meal, which tells you something about scale that the numbers alone don't quite convey. The rogue black hole Hubble caught a few years ago is the observation that keeps nagging at me: 1 billion solar masses moving through intergalactic space at 1,300 miles per second. Something ejected it from its home galaxy. These events aren't anomalies, they're just events we happen to catch evidence of. The universe has been running these dynamics for 13 billion years. Collide all of them at once. And the cascade works roughly like this. Mass hierarchy determines outcome. Bigger absorbs smaller. The resulting object is more massive and pulls in the next candidate faster. Repeat. Each merger produces gravitational waves. LIGO detected waves from a merger over 1 billion light years away. And even after traveling that distance, the signal physically moved our detectors by less than the width of a proton, but moved them. A simultaneous all-black hole merger event wouldn't produce gravitational waves so much as a gravitational convulsion. I don't know what word would be appropriate. I'm not sure the physics has one yet. Run it far enough forward and you get a single object, everything that was compressed into one thing, then Hawking radiation. This is the part where I have to be honest. We've never observed Hawking radiation. The mathematics is compelling, and most physicists take it seriously, but it hasn't been directly confirmed. We're extrapolating the final evaporation scenario, the last black hole slowly losing mass until it winks out, is real in our models. Whether it's real in the universe is a question we may not be able to answer experimentally. The Andromeda collision in 3.75 billion years is not hypothetical in the same way. The trajectory is established. The galaxies are approaching. Whether anything is alive to catalog this is genuinely unknowable. Here's what I find myself stuck on. The models stop producing output at a certain point. Our equations break down as different from nothing happens. One is a statement about mathematics, the other is a statement about reality. Right now we can't reliably tell which one we're making. That's not a satisfying place to end, but it's where the science actually is.